Hello, my name is Bob DeHilster, and I am your particle model guru. Today I'm going to talk about objects moving faster than light and compare that to a function called drag. So let's look up faster than light in Wikipedia. Faster than light, also called superluminal, luminous meaning light, superluminal, faster than light communication and travel refer to propagation of information or matter faster than the speed of light. Now, the theory of special relativity implies that only particles with zero mass, rest mass, may travel at the speed of light. They say nothing else can go faster than that. Although they had proposed tachyons, that particles whose speed they claim it would exceed that of light, but the existence of such particles would violate causality, and the consensus of physicists is that such particles cannot exist. So special relativity is telling us that you can't go faster than the speed of light. Now these are equations you get anywhere. I got it from this particular link. And it's the result of deriving equations which talk about time dilation, length contraction, and mass increase. Now, in this equation, you're really comparing the velocity of the object with the speed of light. The closer you get to the velocity of light, as v approaches the value of c, this term becomes 1. This approaches 0. So as your speed increases, regular time changes, it gets slower and slower until time stops. It's called time dilation. You've got the same effect on length. In an object, the faster an object goes, the closer this term goes to 0, length goes to 0. And then mass is different. By the way, this is length contraction. Mass is different because it uses the same term, but it's in the denominator, such that as this term goes to 0, mass increases to the point where at speed c, mass is infinitely large. So here's a strange thing about special relativity. You have an object and it's moving at speed c, and so it's going to be moving at speed c, and it's by the time it gets to speed c, time stops. However that happens, length contracts, which means it's going to take this object and shrink it down smaller and smaller until it's almost nothing, virtually nothing at speed c, has no size, and yet the mass is infinite. It's huge, it's big. Time stops, volume is 0, mass is infinite. A rather unusual circumstance for an object moving at speed c. I digress for a moment. At the John Chappell Natural Philosophy Society in 2016, I wrote a paper titled "Special Relativity is Not Needed." It's the only paper I've ever written on special relativity. You can get a copy of that paper at the CNPS website, and there's the link. You type that in, you'll get the paper, and then you can read it for yourself. There is also a video presentation of this when I did it at the conference, and you can watch the video presentation of that paper by going to this link. My one and only paper I'll ever write on special relativity or relativity in general, because I have so much I'm doing with the particle model. So let's talk about some of the known values of the speeds of the planets, speeds of the stars, speeds of comets. Let's go through that and see what we have. This is a graph off the internet showing the speeds of Mercury, which is closest closest to the sun, all the way out to Pluto, which is furthest from the sun. And you can see that we have something with Pluto somewhere maybe 5, maybe more than 5 kilometers per second, all the way up to Mercury, which is getting close to 50 kilometers per second. That's the known speed of the planets going around the sun. I presented this graph in my last presentation, and it shows the speed of the stars in our galaxy. And they go slow right near the core, but it gets up to around 240, almost 300 kilometers per second. The stars going that fast. And the speed of the comets. I got this information about comets as it tracks past the Earth's orbit. And what they do here, and I won't read the whole thing, is they take its highest speed at perihelion, which is over here, and its lowest speed at aphelion, and then you divide it by 2 and you get an average value of the speed of the comet as it comes through the Earth's orbit. Typically for a comet then that is about 1 astronomical unit, the distance of the Earth from the sun, if it's that far away, it would have a speed of around 10 to 70 kilometers per second, which varies around the speed of the Earth, which in this article they say 25 kilometers per second. So in summary, we have special relativity. Odd things happen when the object approaches the speed of light. Time stops, volume goes to 0, mass goes to infinity, whatever that is. In observable objects that we see, we have anywhere from 5 to 50 kilometers for planets, up to like 240 kilometers per second for stars, and comets 10 to 70. But light goes about 300,000 kilometers per second, using similar terms so we can compare the speeds of things that we know about and see. At the particle level, it's different. In particle accelerators, they can apply 7 tera electron volts to a proton and get it to go almost to the speed of c, which is somewhat hard to believe when you look at special relativity equations. At that speed, the mass has got to be huge, and the fact that it can even get there is remarkable. The neutron, with the energy of 15 million electron volts, gets speeds of only 54,000 kilometers per second. Well, that's 300,000 kilometers per second for light, which is I showed earlier. Okay, regardless, however, this tera electron volts is 1,000,000 times larger. Well, 500,000 times larger than the force they use on the neutron. The electron, I found in the internet, the electron orbital speed is around 2,000 kilometers per second. They claim it's the speed of c divided by the fine structure constant. And that's, if this were 150, this would be approximately 2,000 kilometers per second, is what they're saying it is, which is much slower. That's as opposed to 300,000 for light. In a circuit, and specifically in an alternating circuit in copper, they say that the electron is going at 3.2 meters per second. Wow, how slow is that? Now, the speed of the gravity, which is generally called the graviton, Newton and his contemporaries thought the speed of gravity was instantaneous. It's called instantaneous action at a distance. That means it's infinitely fast. That's what they thought it was, or that it had to be based on their observation of the planets going around the sun. Even though they didn't like it, instantaneous action at a distance, nobody likes it, but that's what it seems to be. However, in 2012, in a Chinese bulletin, there was a report that a scientist did a measurement during an eclipse of the speed of gravity, specifically from the moon during that eclipse, apparently. I've read it. You can find it on the internet. And they claim they actually measured the speed of gravity at sea. Okay, that's what people say. That's what you can find on the internet and read about. What does the particle model say? Well, there are three main particles in the particle model. I've said this over and over again. There's the nucleon, there's the G1, and the G2. The nucleon and the G1 make up objects such as atoms, molecules, and larger objects, planets, stars, and comets. So our atomic structure is made from the nucleon and the G1, as proposed by or suggested by the particle model. The G2 particle is responsible for refraction. That's when I talked about two gravities. In the presentation on two gravities, and I looked at refraction, it suggested to me that there is a second gravity. And because I am prone to talk about particles, it suggested to me that if the G1 is the graviton and the gravity particle, the G2 then must be the second gravity. That's the particle. So let's talk about light. The speed of G1 is light. G1 replaces the photon. The photon is the name of the light as a particle. The photon also has wave properties, and I'm going to get to that in the next presentation. Photon has wave properties, but it's also treated as a particle, and it moves at or about the speed of c. Now that phrase, at or about the speed of c, is a phrase I'll use over and over again because the speed of this particle can change. It can be accelerated and decelerated, and I'll talk about that in a moment. Here's the value. That's supposed to be a period, not a comma. C, the precise known value, or I think it's the statistically averaged value, is close to 300,000 kilometers per second most of the time. But because of external forces, in my opinion, it can move slower or faster than c. But the G1 orbital, the fact that the electron orbits the nucleus of an atom, or in the particle model, the G1 orbits the nucleons, this is key. The particle model suggests the electron, this is the first comment right here, the G1 orbital moves around all atoms at or about the speed of c. Making that assumption initially, and then over time, hopefully, you'll see why that is true. Specifically, the electron, which is a G1 orbital in the atoms of the battery. You go to what the battery is made of in the anode and the cathode. There are electrons there, or in the particle model, there is G1 particles orbiting the atoms of the battery. And when they're released from the battery, they will be moving at or about the speed of c because they start as orbitals. The photon is the G1 orbital of the atoms in the sun. We have atoms in the sun. They have the photon is, in our model, orbits the atoms in the sun, although we call it the G1 particle, is orbiting atoms in the sun and is released from the sun at or about the speed of c. And the graviton is the G1 orbital, also in the atoms of the sun, is released also at or about the speed of c. Difference between the particle model of light and the particle model of gravity is one of the very first rather informal presentations I gave, which stated that it's the organization of the G1 particle as a stream of particles with a repetitive pattern, whereas the gravity, when the gravity particles are random and moving in all directions and do not have this organization. The orbital is the key to all of this. Let's talk about drag. Drag is caused by particles hitting an object and slowing it down. So here, let me just go to a different presentation. And what I'm going to do here is I'm going to say I got a particle that is moving in this direction, and my thumb, I got an object moving in this direction, and I got a particle, which is my thumb, trying to catch up with the particle, with the object. They're both moving at the same rate, and it's trying to, so if I hold it steady, it's going to look like it's slowly catching up and finally pushing. Not very strong, a rear end collision. On the other hand, if I move the same particle that same direction, or object that same direction, and the I get this straight here, and the particle, my thumb, is coming at it, they're going to be coming, bang, they're going to come real fast, hitting real hard. Head-on collisions are strong. Rear-end collisions are quite weak. It's a combination of those two effects which will slow an object down. The rate at which it slows is proportional to the difference between the speed of the object and the speed of the particle. That's important in terms of how much slowdown a particle, an object will have. Okay, now let's talk about speed in open space. If space is truly open, then any object that is at rest or moving at constant velocity will continue to be at rest or move in a straight line and at constant speed. Okay, this is actually Newton's first principle. It's called inertia. In open space, and basically that's what kind of way Newton thought about it. In open space, there is nothing there to cause the object to change its speed or direction, so it stays in a straight line and it moves in constant speed, or if it's at rest, it stays at rest. But in the particle model, we have these G2 fields, and I told you, I explained a little bit, a couple of slides before, that the G1 and the G2 come from the stars in our galaxy in the universe. But the particle model suggests that the open space is really permeated by G1 and G2 fields. I'm going to call them fields, and there is open space between all of these particles, both G1, G2, and with each other. G1 particles move at or about the speed of c, coming from many different stars, and move in random directions. This is what we call the G1 particle field. G2 particles have a very high speed, I'm going to suggest c squared, coming from many different stars and moving in random directions. This is the G2 particle field. So there is open space between these particles, but the space is permeated with these two fields. How about the speed of the G2 particle? In my presentation on two gravities, I suggested that gravity is what caused refraction. That is, we saw G2 bending light, and causes the G1 causes the G1 particle to orbit the nucleus. To do this, it must move faster than light, faster than c. In other words, if the particle is going to catch up to light, which is already at c, it can't push it faster unless it's moving faster than c. So to bend light, or to cause it to accelerate, G2 must be faster. To cause the G1 particle to orbit the nucleus of an atom, it must be moving faster than the particle itself. And if the G1 particle is orbiting the atom at or about speed c, then G2 must be faster in order to set up the G2 gravitational field that holds the G1 in orbit around the nucleus. How fast does the G2 go? I really don't know. Must be really fast, and I'm suggesting c squared and maybe more, or it will cause light to slow down as it drag. And although there are some concepts about what's called tired gravity or tired light, uh, basically we don't observe, at least I don't know of anything that where we observe light slowing down significantly. If light doesn't slow down, then G2 has to be extremely fast. The speed of the nucleon, this is the final third particle. We've covered G1 now first, then G2. Now the speed of the nucleon is less than c. We see that in the data, presented that at the beginning. Nucleons in atomic matter must pass through the G1 and G2 fields. In particular, as the nucleon and atoms pass through the G1 field, it would cause drag and slow these objects down, not letting them get to the speed of c, because the faster then the nucleon goes, the harder it's being pushed back, and the less it's being pushed forward, it's going to slow down. G1 gravity will keep the speed of the nucleon, the G1 field really, and gravity, will keep the speed of the nucleon and atoms below the speed of light. Our conclusion, the particle model conclusion is that nucleonic matter will not go faster than light. G1 particles move at or about the speed of c, and G2 particles move much, much faster than the speed of light. Unfortunately, what this says is man and spacecraft, items made from atoms, which contain nucleons, will not move faster than light. But G2 does. So my name is Bobby Hilster, and I am your particle guru. Tune in next time when I will explain more of the universe using the particle model. Thank you for your attention.